The last colligative property we're going to talk about is Henry's law. Henry's law governs the solubility of gases. We've been talking about dissolving solids into liquids or combining liquids. Now we finally talk about gases dissolved in a liquid. Now, what Henry's law says is that the concentration of the gas in a liquid is proportional, through the Henry's law constant, to the partial pressure of the gas above the liquid. Why do you care? Well, if you have ever had a goldfish and you noticed that it was gasping at the surface of the water, it was probably because the water had gotten too warm. Well, what does that have to do with it? It doesn't say anything in here about temperature. But it turns out Henry's law constant is the most ill-named constant ever, because it's not constant. It depends on temperature. So it would really be better to call it a Henry's law factor, because yes, it definitely is a factor. You're multiplying things together here. But they call it the Henry's law constant despite this. So this concentration of the gas, maximum concentration in that particular solvent, the Henry's law constant is governed by the gas, not the solvent. That's different than what we've seen in these other equations. And P of the gas is the partial pressure of the gas above the solvent, because you usually have a mixture of gases. I mean, if we're talking about normal air, we're always talking about a mixture of gases above the liquid, the solvent. Why do we care about this? Well, again, not just goldfish, also people. The concentration of oxygen in your blood is going to be proportional to the partial pressure of oxygen in the air that you inhale. This is why when people go and they climb Mount Everest, they end up having to take oxygen tanks with them, because as you go higher up in the atmosphere, you have less pressure. So even though there's just as a percentage, there's still 25% approximately of oxygen, it's 25% of a much lower pressure, and so the partial pressure is consequently lower as well, and it ends up that your blood is not getting sufficient oxygen to operate all of your organs properly. So this is why mountain climbing can be particularly hard. So the solubility of gases in a liquid almost always decreases with an increase in temperature. That's different than what we're used to when we're dissolving solids. We think about dissolving solids and we think, oh, if we raise the temperature, we'll get more to dissolve. Like when I have my tea, if I'm going to make sweet iced tea, I don't make iced tea and then put the sugar in. I make hot tea, I put the sugar in, dissolve it, and then I cool it down, because that way I can get more of it to dissolve. But gases, almost all of them, are the opposite way around. If you increase the temperature, fewer gases are going to dissolve in the liquid. And that's why you find the goldfish gasping at the surface of the water when it's very hot, because there's not enough oxygen dissolved in the water. And the goldfish says, well, I'm just going to go for the straight stuff up above here. And now we'll work a little puzzle. You know, you could go buy a 1 liter bottle of soda pop. We have a pressure, and it says it's 44 psi, and that is happening at 20 degrees Celsius, and they want to know how much carbon dioxide is dissolved in the seltzer. And they want the answer in grams. And then fortunately, they're giving us some references. They're telling us that an atmosphere is 14.7 pounds per square inch. And they told us, if we went and looked at a table in the book, that the Henry's law constant at 20 degrees Celsius is this number. Okay, and you see that these units are all going to work to make the Henry's law work out. We want to rearrange some stuff. Concentration of the carbon dioxide is going to be K sub H, and the partial pressure of the gas above it. Well, fortunately, they told us the partial pressure. Unfortunately, they told us it was in PSI. So 44 PSI, so I will multiply this. I will put the pounds per square inch on the bottom, so it'll cancel out, and I'll put the atmospheres on top. So there we go. Now it's going to be an atmosphere 2.99. Ooh, maybe I should have done 3 because, you know, But you know what? I'll keep the extra sig figs all round back at the end. So there's the pressure that I'll be using right here. That means I can just go ahead and put in the number they told me for this Henry's Law constant. 3.5 times 10 to the negative 2 moles per liter an atmosphere. And then I'll multiply by the 2.99 atmospheres. And I'll see it's moles per liter, so I have a concentration. Here's my concentration in moles per liter, but that wasn't what they asked me for. They asked me for how many grams of CO2 was dissolved in the seltzer. It says it's a 1 liter bottle. Aha! If it's a 1 liter bottle, I can just multiply the 0.105 moles per liter and multiply it by the 1 liter bottle. Now I know how many moles there are. So this is moles of what? Carbon dioxide, that's what. They want it in grams. Okay, I go look up what is the molar mass of carbon dioxide? 44.01 grams per mole. And I will multiply these together, cancel the moles. And now I'm going to go ahead and round it back to the 2 sig figs. 4.6 grams of carbon dioxide. That's quite a bit. No wonder when you open it up, it starts fizzing and forming all those bubbles. If you've stuffed that much in there and now you release the pressure, then the amount that can stay dissolved is going to go down because the pressure went down. That's going to go down. And all these are start bubbling out, and that's why your soda pop fizzes.